Okay, I thought I'd give some hints on the homework problems. These aren't worked out solutions, but rather just the direction to go in case you're getting stuck on problems because it's just more difficult to talk during office hours, so maybe this will get you unstuck on some of them. Let's just start from the beginning of the chapter 6 homework. Here's problem 1. We have a block with a given mass, has a given initial speed at time t equals 0, and slides on a horizontal surface. Find the work that must be done on the block to bring it to rest. So in this case, we have something that sounds like a particle, so we may as well take our system to be just the block, and we can use the work kinetic energy theorem to find the net work that must be done is equal to 1/2 mv final squared minus 1/2 mv initial squared, and of course v final is 0, so the answer is just going to be 1/2 mv initial squared, which would be the work that has to be done. Problem 2, which is part 2 of that problem, if a constant friction force of magnitude 12 newtons is exerted on the block by the surface, find the magnitude of the acceleration of the block. So here I think we're supposed to assume that the friction force is the only force that's bringing it to rest. So that net work in part 1 is being done by the friction force. So in this case, we can, if we want to find the magnitude of the acceleration of the block, well, in this case, we could just say we know the magnitude of the force, and that's the only force with an x component. Of course, there's a normal and a gravitational force, but those won't have a horizontal component, so we can use F net x equals max, and using that find the acceleration of the block. So that's not really an energy problem, part 2, but we might use it here in part 3. How far does the block slide before it comes to rest? We could do this problem using kinematics, but I don't want to do that because we're in the section on energy. So of course we could use the acceleration and then use constant acceleration kinematics, but instead let's use the work kinetic energy theorem. We already calculated the net work that has to be done on it up here in part 1. So in part 3 we can do the magnitude of the force, the friction force, which is 12 newtons, and that friction force is doing negative work. So negative 12 newtons times delta x, that's our fx times delta x, and fx is negative here if x goes along the direction it's moving. Minus 12 times delta x is equal to 1/2 mv final squared minus 1/2 mv initial squared, and we know v final is 0, and that allows us to solve for delta x, which is how far it slides in problem 3 there. Now, problem 4, cart loaded with bricks has a total mass of so many kilograms and is pulled at a constant speed by the rope. The constant speed is probably important here. The rope is inclined at 22.1 degrees above the horizontal, so we're sliding something on the horizontal floor, but pulling with a rope that's inclined to the horizontal. And the cart moves along the floor a distance of 23.1 meters. The coefficient of kinetic friction is given, and we're asked how much work is done on the cart by the rope. And I guess I should point out before I forget, it's asking for the answer in kilojoules, so you will be tempted to get the answer in joules. Just divide by 1,000 to put it in kilojoules. If we want to know the work done on the cart by the rope, we know how far it's gone, right? That's the 23.1 meters here. So we're going to use the formula Fx times delta x, and Fx is going to be the tension in the rope times the cosine of 22.1 degrees would give me the x component of the tension, times the distance it moves along the x direction is 23.1 meters. And so Fx times delta x, or tension x times delta x, would give us the answer. The only question is, what's the tension in the rope, or what is the tension x component in any case? And I can do that by balancing x components of the forces. We're told it's moving at constant speed up here, and therefore the friction force magnitude, mu kinetic times the normal force, which is just mg. I'm sorry, it isn't just mg in this case. We have to first find out what the normal force is, and the normal force involves, well, let's see, I have mg going down, I have a normal force going up, which I'm going to solve for, and I also have a vertical component of the rope force, which would be the rope force times the rope tension times the sine of 22.1 degrees, and that would involve the unknown normal force and the unknown tension of the rope. That's sort of balancing or setting the sum of the force y components, where y is vertical, to be 0. And then also I could write down the sum of the force x components equals 0, because it's not accelerating at all here. And the sum of the force x components would be the tension T times the cosine of 22.1 degrees minus mu kinetic times the normal force is equal to 0. And those two equations give me two equations in the two unknowns, which are the tension and the normal force. And I could use that to find the tension. We don't really need the normal force in this case, but I would use that to find the tension. And then the work done on the cart by the rope would just be the tension times the cosine of 22.1 times the horizontal distance it slides, which is 23.1 meters in my problem. So that's our Fx times delta x. Convert to kilojoules. On each diagram, a block is acted upon by a force of magnitude F in the direction shown. So here are 4 different situations, same magnitude force in all 4 of those, but the force is pulling in different directions. And we're told the block undergoes the same displacement to the right in the diagram, and it only moves to the right. Which of the following is the correct order of the amount of work done by the force F, from most positive to most negative? So the block is moving to the right. This one's going to do positive work, so this will be the only positive one, so I guess C would be first. Then this one would do 0 work up here, so in mine I would have A. Then this one does slightly negative work because it's only the negative x component of the force would be our Fx. If x is the direction it's going, Fx would be a little bit negative there. And here Fx is even more negative, so first C, then A, then D, then B would be the most negative. D and B are both negative, but B is more negative than D. 6. Baseball is hit high into the upper bleachers of left field. As after the ball lands in the bleachers, the work done by gravity and the work done by air resistance respectively will have been, it looks like we're looking for what signs they have, positive or negative. None of them is 0, but the baseball is hit high into the upper bleachers. Gravity is doing negative work while the ball is going up, and it's doing positive work while the ball is coming back down, because the gravitational force is more or less along the direction of the displacement on the way down. But it doesn't go down as far as it goes up, so it does gravity does a lot of negative work on the way up and a little bit of positive work on the way down. So the gravitational work is going to be overall negative. That narrows it down to selections 2 or 4. And the air resistance force always pushes against the direction the ball is moving, so it certainly is pointing more or less opposite the direction of the displacement the whole way out there on the way to the upper bleachers. So the air resistance force is also going to be negative. So in my accounting here, it looks like my answer 4 would be the correct answer. Block on a surface, problem 7. A 3.09 kilogram block at rest is pulled to the right on a horizontal surface by a constant horizontal force of 15.9 newtons. Sounds like it might be accelerating here, so we want to keep that in mind. We're given the coefficient of friction. Find the speed of the block after it has moved 4.29 meters. Again, we could do this problem using kinematics. We know how far it goes. We know it starts from rest. We want to find its final speed, so we could use a kinematics equation to do that, the v squared equation. But rather than that, let's use energy methods to solve this. The work kinetic energy theorem, if I treat the block as my system, it certainly is a particle type system, and so the net work done by all forces on it is equal to the change in kinetic energy of the system. And in this case, the pulling force, 15.9 newtons, is going to do positive work on it, so it would do a work of 15.9 newtons times 4.29 meters, whereas the friction force is going to do negative work, so I have to add on to that positive work some negative work, minus mu kinetic, 0.135, times the normal force, which in this case would just be mg, because nothing else is pushing or up and down on the block. So mu static times, mu kinetic times mg would come in with a minus sign. So I add those two works together, that would be the net work done on the system. Gravity's not doing any work, and the normal force isn't doing any work, so those just contribute 0 because they're perpendicular to the displacement. So that net work is equal to 1/2 mv final squared minus 1/2 mv initial squared, and the final will be when it's moved 4.29 meters. So I want to solve for that v final, and our v initial is 0 because it's initially at rest. Solve for v final. Problem 8. Two students ride in carts opposite to one another in a spinning Ferris wheel as shown. Student A originally at the bottom of the Ferris wheel, while B is at the top of the Ferris wheel, and then they flop positions. A rides up to the top, B rides down to the bottom. Okay, here they are in their final positions after going a half revolution. The Ferris wheel spins at a constant speed, so the two students are traveling with constant speed. Student A and B have masses ma and mb respectively. The Ferris wheel has a radius r. What is the magnitude of the total work done on student A in moving from the bottom to the top of the Ferris wheel? Well, in this case, if we're talking about the total work, I guess they mean the net work in this case. That's just a different name for it. The net work is equal to the change in kinetic energy of student A, and student A is moving at the same speed at the bottom as they were at the top as at the bottom, and therefore the change in kinetic energy is 0, and therefore the net work is 0. So it seems like that's my selection 3 here among all of them. That was easy. And then part 2 of 3, what is the magnitude of the work done on student B by the Ferris wheel in moving from the top to the bottom? So B is riding down to the bottom. The Ferris wheel more or less is pushing up on the student with a normal force from the seat. So the seat, or the Ferris wheel, is pushing up on the student as the student is having a displacement down going from the top to the bottom. So it seems like it's a negative work to begin with. Oh, I guess that doesn't matter because we're only asked for the magnitude of the work, so forget about the minus sign. But the magnitude of it is the magnitude of the normal force of the Ferris wheel, and the normal force of the Ferris wheel is just going to balance out the weight force. So the Ferris wheel normal force would just be mg, so mass of student B times g, times the displacement magnitude, which is 2r, and going from the top to the bottom, they go through a total displacement of 2 radii. So that looks like 2 mv times g times r, and in my selection here, that magnitude is the very first one to appear. Part 3, what is the sign of the work done on student B by the Ferris wheel in moving from the top to the bottom? Oh, here's what I already did my work for this one. It's doing negative work because that normal force from the Ferris wheel is pushing up on the student as student B is moving down to the bottom. So it's doing negative work. That's selection 3 here. Problem 11, parts 1 through 5. A crate is pulled up a rough incline. The pulling force is parallel to the incline. The crate is pulled a distance of 5.14 meters. What is the magnitude of the work? What is the magnitude of the work done by the gravitational force? Okay, in this case, to calculate our answer here, the gravitational force of course, is going to do negative work, but we don't want to put a minus sign in because they're asking for the magnitude of the work only. So we want the magnitude of the gravitational force along the incline direction, and that would be mg times the sine of 30.8 degrees. That a diagram would help there. Would give me the component of the gravitational force along the direction of motion, and then multiply that by the displacement it moved along the inclined direction times 5.14 meters would give you the magnitude. No minus sign, even though gravity's doing negative work. Oh, good. I've already worked out this one. The work done by the gravitational field is negative. That's what I just said. Don't put that in the previous one. They're not looking for a minus sign there because they asked for the magnitude. But here the answer is negative. Part 3, problem 13. How much work is done by the 167 Newton force? Well, it's pulling along the direction of the incline, so we just do 167 newtons times 5.14 meters, okay? And that would be positive in that case. 14, what is the change in kinetic energy of the crate? So in this case, we could figure out, I guess, what we need to do is figure out what the net work on it is. We're not given what the final speed is, but we can figure out what the net work is. There are 3 forces doing work on the block if we treat the block as our system and just try to use the work kinetic energy theorem. We've already calculated the positive work done by this pulling force. There's some negative work done by the gravitational force. There's also some negative work done by the frictional force. Okay, this is a rough incline. And so what we need to do is figure out what the magnitude of the friction force is. That's a balancing forces kind of argument in this case. So we would use F net y, where y is perpendicular to the plane direction, equals may to find the normal force, and then use mu kinetic times the normal force to get the magnitude of the friction force, and then that magnitude of the friction force with a minus sign times the 5.14 meters would give me the negative work done by friction. I have to add all 3 of those works together, 1 positive and 2 negatives, and set that number equal to 1/2 mv final squared minus 1/2 mv initial squared. And in this case, I'm looking for something that tells me that this crate is starting at rest. I don't see that, but since they don't give us an initial speed, it seems like we're supposed to assume that it starts from rest. Oh, no, here we go. I'm not sure where does that come into the text there. It looks like its initial speed is 1.5 meters per second. So when we do the work kinetic energy theorem, add all those works together, set it equal to 1/2 mv final squared minus 1/2 mv initial squared, and use 1.59 as my v initial, and then solve for v final. That would give me the speed, the final speed of the crate after it's moved that distance up the plane. And I guess along the way we could calculate the net work would give us the change in kinetic energy. So when I calculate my net work, that would give me the answer to 14, and set that number equal to 1/2 mv final squared minus 1/2 mv initial squared to get the answer to 15. 16. A bobsled is pushed on a horizontal surface by 2 athletes. After the bobsled is pushed a distance of 6.8 meters, starting from rest, its speed is 8.6 meters per second. Find the magnitude of the net force on the bobsled. So in this case, we could use kinematics again in this case because we could figure out its acceleration. But in this case, let's try to use energy methods. And again, this seems like a nice one to use. I know I'm sticking to the work kinetic energy theorem, but it's actually easier to talk about without writing things down. So in this case, if we treat the bobsled as our particle system and apply the work kinetic energy theorem, in this case, we know that its final speed is 8.6 meters per second squared, and its initial speed is 0. So if I do 1/2 mv final squared minus 1/2 mv initial squared, I can calculate that number and set it equal to F net x times delta x. And our delta x in this case is 6.8 meters, and solve for F net x. That would give us our answer in newtons. A 13 kilogram crate is pulled up a rough incline with an initial speed of 1.4 meters per second. The pulling force is 111 newtons, parallel to the incline, which makes an angle of 14.1 degrees with the horizontal. So it kind of looks like this situation over here, except there's a different angle and different numbers associated with things, but it looks like that situation. Coefficient of kinetic friction is given. The crate is pulled a certain distance up there. Find the work done by Earth's gravity on the crate. This is definitely a negative work because it's going up the plane while gravity is pulling down on it. So what I do is find the component of the gravitational force along the direction of the plane, and then put a minus sign in front of it times that friction force plane parallel to the plane component times the distance it goes, which in my case is 8 meters. Okay, that's going to be a negative work done by gravity. Part 2, find the work done by the force of friction. In this case, I have to find the force of friction, which means I first have to sum forces equal to 0 along the direction perpendicular to the plane, find out what the normal force is, and then do mu kinetic times the normal force is the magnitude of the friction kinetic force, minus sign times that kinetic friction force times the distance it moves is going to give me that negative work done by the friction. Find the work done by the puller on the crate. In this case, we know the magnitude of the force, 111 newtons, so it would just be 111 times 8 meters would give me the work done by the puller. Add all those together, we get the net work done on the crate by all forces, and that's equal to the change in kinetic energy of the crate, and so we can calculate that net work, and that is equal to the change in kinetic energy of the crate. And then if we find the speed after the crate is pulled 8 meters, that would be setting that number equal to 1/2 mv final squared minus 1/2 mv initial squared, and we were given a v initial in the problem, so we could find out what v final is that way. Here a bullet is moving very fast, penetrates a tree trunk and goes to a depth of a few centimeters. Use work and energy considerations to find the magnitude of the force that stops the bullet. So we'll assume a constant magnitude force stops the bullet, and we know its final speed is 0, its initial speed is given there, and its mass is given. Change everything to SI units, of course. And then use the net work is equal to 1/2 mv final squared minus 1/2 mv initial squared, which we can calculate, and that is equal to the net work force x component times delta x, and our delta x is 0.0373 meters, and so we can solve for the net force x component that is doing the work. Here we're assuming it's not really a friction force, but you're compressing the wood, and also there's some friction on the wood, so that would give us the magnitude of the force that stops it. Part of it's due to the scraping of the wood as it goes in, but it's also pushing on the wood in front of it, so the wood's pushing back on it in several ways, friction and compression. Part 2, or B, assuming the frictional force is constant, determine how much time elapses between the moment the bullet enters the tree and the moment the bullet stops moving. We can't really find anything about time from energy considerations, so we really have to go back to kinematics here and say, well, I could use our Vx equals Vx0 plus Ax times t. Solve for A, because we already found F net x up here, so we could solve for Ax using F net x equals Max. So we know Ax, and then we know Vx initial is equal to this speed that's given. Vx final is 0, AX would be negative if we're calling the Vx positive initially, and then solve for t in Vx equals Vx0 plus AX times t, our old kinematics equation. Finally, problem 24, we have a very heavy pile driver is used to drive an I-beam into the ground. What this means is you stand a beam on its end and get a little bit of way into the ground. You want to drive it down into the ground, but it takes a tremendous force to do that. So what you do is take a big hunk of metal, like a big, huge iron cylinder, raise it up with a crane and drop it so it slams down on top of the I-beam and it drives it a small amount into the ground. You keep repeating that over and over again, and you can get a huge beam really deep into the ground, which keeps it from ever moving after that. So here it falls onto it, falls a distance 4.04 meters before contacting the beam, drives the beam 15 centimeters into the ground before coming to rest. Find the magnitude of the average force the beam exerts on the pile driver while the pile driver is brought to rest. So in this case, I guess we could first do a little kinematics calculation to figure out the speed of the pile driver after it starts initially at rest and it drops a distance of 4.04 meters. That's something we could have done way back when. Find that speed, that initial speed it has right before it hits the beam. And then if I have if I treat my system as just the pile driver, in other words, it is a particle system, I can apply the work kinetic energy theorem in that period when it's coming to rest over the 15 centimeters. And so the net work done by all forces, and there are two forces acting on the pile driver. There's the weight force, the Earth is pulling down on it, but then the beam is also pushing up on it. So gravity is doing positive work as it moves the 15 centimeters, and that beam force is doing negative work. So the net work done by all the forces is equal to the change in kinetic energy. The net work is equal to mg times 0.15 meters minus the unknown force of the beam on the pile driver times 15 centimeters, or 0.15 meters. That's the net work, the sum of those two works, is equal to 1/2 mv final squared minus 1/2 mv initial squared. The v initial is going to be our final speed after dropping the 4.04 meters, and the v final is going to be 0 because that's the speed it has once it's come to rest. And so the only unknown in that problem should be the unknown force of the beam on the pile driver. In this case, we're just asked for the magnitude, so we don't really care about which direction it is, but in any case, put that in newtons.